We now turn to complements and the complement rule, one of the most useful basic tools in probability. If we define an event A, then its complement, written A superscript C, consists of all outcomes in the sample space that are not in A. In everyday language, either the event happens or it does not happen. There is no third possibility. Because those two possibilities together exhaust the entire sample space, their probabilities must add to 1. This simple idea gives us a powerful shortcut for solving many probability problems. Since an event and its complement together account for all possible outcomes, we know that the probability of A plus the probability of A complement is equal to 1. Rearranging this gives the complement rule. The probability of A complement is equal to 1 minus the probability of A. This rule is extremely helpful because sometimes it is much easier to compute the probability that something does not happen and then subtract from 1. Rather than counting many complicated favorable outcomes, we can count a small number of unfavorable ones. This strategy becomes especially useful in at least one type problems. The complement rule shines in situations involving phrases like at least one, at least once, or at least one success. These can be complicated to compute directly because you must account for multiple possible outcomes. But often the complement, such as none or 0 successes, is much simpler to compute. By calculating the complement first and subtracting from 1, we reduce the work dramatically while still arriving at the correct probability. Let's look at example 1 involving 3 coin tosses. The full sample space contains 8 equally likely outcomes. Each of these sequences has probability 1/8. Suppose we wanted the probability of getting at least 1 head. Counting all sequences with at least 1 head would require listing 7 different outcomes. Instead, we use the complement rule. Define A as the event at least 1 head. Then the complement is the event no heads, which means all tails. There is only 1 outcome with no heads. Therefore, the probability of the complement is 1 divided by 8. Now we apply the complement rule. So the probability of A is equal to 1 minus 1/8, which equals to 7 eighths. That was much faster and cleaner than counting 7 favorable outcomes individually. Next, we move to combining events using unions and intersections. When we talk about the union of 2 events, we mean outcomes that are in A or in B or in both. In contrast, the intersection of 2 events contains only those outcomes that are in both events simultaneously. Understanding the difference between or and is critical in probability because these lead to very different calculations. The general addition rule allows us to compute the probability of a union. It states that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. The subtraction term is essential. If we simply added probability of A and probability of B, we would double count the outcomes that belong to both events. Subtracting the intersection corrects for that overlap. This formula works for any 2 events, whether or not they overlap. Now consider example 2, involving beverage preferences. Out of 200 students, 120 like coffees, 90 like tea, and 60 like both. Let C represent liking coffee and T represent liking tea. Converting to probabilities, we find the probability of C equal to 0.6, the probability of T is equal to 0.45, and the probability of C intersection T is equal to 0.30. We want the probability that a randomly chosen student likes coffee or tea or both. Applying the addition rule, we compute the probability of C intersection T as 0.60 plus 0.45 minus 0.30, which is equal to 0.75. So 75% of students like at least one of the 2 beverages. Notice why we subtract 0.30. When we added 0.60 and 0.45, the 60 students who like both coffee and tea were counted twice, once in each category. Subtracting the intersection removes that double counting and gives the correct answer. Sometimes events are mutually exclusive, also called disjoint. This means they have no outcomes in common. If two events are mutually exclusive, then the probability of their intersection is equal to 0. In that case, the addition rule simplifies the probability of A plus the probability of B. There is no overlap to subtract because the events cannot occur at the same time. For example, when rolling a die, let A be the event of rolling a 2 and B be the event of rolling an odd number. Since 2 is even, these events cannot happen simultaneously. They are mutually exclusive. So we simply add their probabilities, 1/6 plus 3/6, which is equal to 2/3. Because there is no overlap, no subtraction is necessary. And consider example 3 involving hospital patients. We are told that 12% are admitted for surgical treatment, 16% for obstetrics, and 2% receive both. Let A represent surgery and B represent obstetrics. Since some patients receive both treatments, the events are not mutually exclusive. Therefore, we must use the full addition rule. Applying the formula, we compute 0.12 plus 0.16 minus 0.02, which equals 0.26. So 26% of patients receive surgery, obstetrics, or both. Again, subtracting the overlap prevents double counting the 2% who receive both treatments. This example reinforces the importance of identifying whether events overlap before applying a probability rule. Finally, let's discuss probability from contingency tables. When we have data organized by two categorical variables, we can estimate probabilities directly from cell frequencies. The basic principle is simple. Divide the count in a cell by the total number of observations. This allows us to compute marginal probabilities, joint probabilities, and union probabilities using real data rather than theoretical models. In example 4, we examine a contingency table involving pulmonary embolism and a D-dimer blood test. Out of 10,000 patients, 1,000 actually have PE. So the marginal probability of PE is 1,000 divided by 10,000, which equals 0.1. If 700 patients both have PE and test positive, then the joint probability is 700 divided by 10,000, which equals 0.07. These probabilities come directly from dividing counts by the total. And to compute a union from the table, we again apply the addition rule. Substituting the values gives 0.10 plus 0.20 minus 0.07, which equals 0.23. So 23% of patients either have PE, test positive, or both. This example demonstrates how complement rules, addition rules, and contingency tables all connect into one consistent framework for computing probabilities from either theory or data.